This is part 2 of the walkthrough of the AQA GCSE 2023 Physics Higher Tier Paper 1. Question 6. A student investigated how the current in a filament lamp varies with the potential difference across the filament lamp. Figure 6 shows the results. So we've got a line graph which is showing us the current on the y-axis and the potential difference on the x-axis. We can see that it begins with a negative potential difference, generating a negative current, and as the potential difference starts to increase, the current starts to increase, and then as the potential difference becomes positive, the current still begins to increase, but then seems to start to slow down in its increase. 6.1. Describe a method the student could use to obtain these results. You should include a circuit diagram. So this is investigating the relationship between current and potential difference, which is a required practical. So the first thing that we need to do is we need to describe a method, but I think we should start with our circuit diagram first. So going back to the graph, we need to be able to measure the current and also measure and change the potential difference. We need to change the potential difference because it's on the x-axis, so that means it's going to be our independent variable. That means our dependent variable would be the current. So we need to remind ourselves then what is going to measure the potential difference and what will measure the current. So our voltmeter will measure the potential difference, and our symbol for a voltmeter is such. And our ammeter will measure the current, and here is our symbol for our ammeter. So we're expecting to put those in our circuit. Remember that we're investigating how the current in a filament lamp varies the potential difference. So we need to make sure that we have a filament lamp in our circuit, and there's our symbol for a filament lamp. So we've got 3 pieces of equipment, 3 components that we're definitely going to put in our circuit. Remember that we need to change the potential difference. So how could we change the potential difference? Well, we could change the potential difference by either using a power supply where we can adjust it, or we can use a variable resistor. Now I think it would be easier for us to use a variable resistor, so we can put that in our circuit too, and our symbol for our variable resistor is shown here. So we have 4 components that are going to go in our circuit now. We then also need to provide a source of energy, and again that would be a power supply or a battery. So let's try and start to construct our circuit diagram now. We'll put in a battery. And we said that we're going to put in a variable resistor. So let's put in our variable resistor in our circuit. Now, we're going to include our ammeter and voltmeter, but we need to be very careful of how we put the ammeter and the voltmeter into our circuit, or else it won't give us the readings that we want properly. So the rule is, when we're putting an ammeter in a circuit, it must go in series. So here is our ammeter. It's forming our single loop in our circuit. And then it will allow us to get the reading within the circuit for our lamp. But our voltmeter needs to be placed in parallel across the component that we are interested in. So we're interested in the lamp, So we need to place our voltmeter across our lamp. And here's our circuit. Now, we're describing the method, of course. So what we want to do then is you want to make sure that we have described this clearly. So even though we've drawn it, let's just state it so we can definitely guarantee ourselves our mark. So the ammeter is placed in series in the circuit. And a voltmeter is placed in parallel in the circuit. Remember, it's across the lamp. Now, what are we going to use the ammeter and voltmeter to do? The ammeter is going to measure the current, and the voltmeter measures the potential difference. Great, so we know what we're going to be measuring now. We then have to go back to our graph, because it says we need to describe a method to obtain these results that come from this graph. Now remember what we said earlier when we were analyzing the graph. The potential difference starts off as negative, and this leads to a negative current. And then the voltage or potential difference becomes positive, and then that would lead to a positive current value. So we need to think now, how are we going to obtain negative potential difference values? Well, remember we put in a battery into our circuit. Remember that a battery has a positive and negative terminus. Now, if we were to reverse the connections in this battery, that would then lead to us getting negative values. So similar to the situation when we were describing putting in a battery into a remote control in the opposite way, of course it wouldn't cause the circuit to work, but if we were recording the potential difference, then it would be negative. So what we would need to say first then is reverse connections to battery or power supply to obtain the negative values. Excellent. So let's look now. We start off with -6, then -5, -4, -3, -2, -1. That's our values are negative. And then our positive values would be 1 volt, 2 volt, 3 volt, 4, 5 volt, 6 volt. So what we can say then is each time we're increasing the potential difference by 1 volt. So that means our interval is 1 volt. We're starting at -6 and we're ending at +6 volts. So that's our range also. So you can say start with potential difference at -6 volts. And increase to +6 volts with 1 volt intervals. Excellent. Now remember, we have put in a variable resistor, and that is how we are able to get this different reading of the current and potential difference. Okay, so we do that up until we get to +6 volts and record our readings. However, what do you want to do to make sure that we can trust the results that we get, ensure that they're reliable? We want to repeat the experiment multiple times and then obtain mean values. So we can say that we can repeat the investigation 3 times, calculate a mean, and then what does mean allow us to do? It allows us to remove and exclude anomalies. And there's our answer. Our circuit diagram is complete. And we describe the method which allow us to obtain values of current and potential difference that satisfy the graph that was shown above. (6.2) Determine the resistance of the filament lamp when the potential difference across it is positive 3.0 volts. Use the physics equation sheet. Use figure 6 on page 18. So, reading the question, they've given us a value of 3 volts, but they've instructed us to use the figure 6, page 18. So if we go back to figure 6 on page 18, that is the graph. So our potential difference was positive 3 volts. So positive 3 volts would be here. What we need to do is read up to our curve and read along to the y-axis. We can see that our interval of our current is 0.01. So that means that our value here on our y-axis for our current when the voltage is 3 volts is 0.16 amps. So let's just make a note of that down below. So our current at 3 volts equals 0.16 amps. Now, what do we need to do? We need to determine, which really means calculate, the resistance of the lamp at that potential difference. So we're using a physics equation sheet. We're looking for an equation that involves current, resistance, and potential difference. And that is our equation for Ohm's law. So potential difference equals current multiplied by resistance. So putting in the numbers into our equation, we have 3 volts, and that will be equal to 0.16 amps multiplied by the resistance. So rearranging, that would lead to 3 divided by 0.16, and we get a value of 18.75 ohms. (6.3) The current in the lamp is 0.21 amps when the potential difference across the lamp is 6 volts. Calculate the energy transferred by the filament lamp in 30 minutes. Use the physics equation sheet, 5 marks. So, we're given 3 values in this question now. We're trying to calculate energy transferred. We're given a current, a potential difference, and a time. So we're looking for an equation that involves all 3 of those values there. Well, there are numerous ways you could approach this. One of the ways in which you could approach this is by using your power equation. Power equals current multiplied by potential difference. So we've got the current 0.21 amps. We've got the potential difference, which is 6.0 volts. If we just plug those into the equation and multiply them, we'll come up with a power of 1.26 watts. Now, we haven't calculated energy transferred yet, but remember that we're trying to calculate energy transferred, but we're given a time also. So an equation that involves power and time, that would be power equals energy transferred divided by time. So rearranging that equation, energy transferred is equal to power multiplied by time. So plug in the numbers in like before. 1.26 is our power, However, our time that's given to us is in minutes. What we need to remember is that our standard unit for time is in seconds. So we need to multiply our 30 minutes by how many seconds in 1 minute? There are 60 seconds in 1 minute, so we need to multiply 30 by 60, and that would be 1800. So we take 1800, plug that into the equation, and that would generate an answer of 2268. Six 6.4. The power output of the lamp is 1 watt when the potential difference across the lamp is 5 volts. A student predicts that the power output would be 4 watts if the potential difference was doubled. Explain why the student is not correct. So, the student is saying that it would be 4 watts if the potential difference was doubled. They've told us that the power output would be 1 watt if the potential difference is 5 volts. Now, the student is saying that before was if it was doubled. Well, if we double the potential difference, that would actually then be 10 volts. So, they're not correct here. Why? Well, let's think about what's occurring now. The power, which is the energy transferred over time, is going to change based on the potential difference. So there is a connection there. Now, if we think about our equations now, the equation that links them is power equals current multiplied by potential difference. Now, what it's saying then is that if the potential difference went from 5 to 10, what would happen to the power? Well, the power would increase definitely, but we're expecting the power to increase based on both the current and potential difference. Well, we're using a lamp in this investigation or in this question. And what will happen if we increase the potential difference to the current? Well, the potential difference will cause the current to increase. Now, what's the equation that links those together other than this power equation? Well, that's potential difference equals current multiplied by resistance. So an increase in the potential difference will cause an increase in the current. But that's provided that the resistance remains the same. But if we go back to our graph, what's happening when we increase the potential difference? The current, as we said before, starts to decrease in this rise. So it starts to slow down in this increase. Now, why is that the case? Well, what happens when you leave a lamp on for too long? It will get hot. And that means that thermal energy is being transferred. That ultimately will lead to resistance. And resistance is the opposition of current, so it causes it to slow down, which is why the line is starting to curve here. So our explanation really then is that there'll be an increase in the resistance, which will decrease the current. Now, what would need to happen for the power to go from 1 to 4. Because if we look at the interval, it's actually gone up times 4, whereas the current has only gone up by 2 times. Now what we can actually do to make this a bit clearer is we can put the numbers into our equation for power here. So what we're saying then is initially we have a power of 1 watt, and we have a potential difference of 5. So something multiplied by 5 would need to equal 1. Well, that would be 0.2. So we need to have a potential difference of 5 and a current of 0.2 to obtain that 1 watt. But if we increased the potential difference to 10, and we got our power to be 4, what would need to happen to the current? Because if it remained at 0.2, 0.2 multiplied by 10 is not 4, that's just 2. So for us to get a power of 4 with a potential difference of 10, we would need to have our current at 0.4. So what that actually means then is not only would the potential difference need to double, the current would need to double also, and we can put that as an answer. So both the current and potential difference would need to double to obtain 4 watts. Question 7. A baby bouncer is a harness attached to a spring that hangs from a door frame. Figure 7 shows a baby and a baby bouncer in 2 positions. Okay, so looking at position A, the baby is above ground, held by the harness. Whereas in position B, the baby is touching the floor, but the spring seems to have extended, gotten longer from the door frame. 7.1. The baby bouncer should not be used with babies that have a mass greater than 12 kilograms. Suggest one reason why. So they've given us a specific value here, 12 kilograms. So what would be the problem if a baby has a mass greater than that? Well, remember that we've got a spring, and that seems to be attached to a chain that's held to the door frame. One thing that probably could happen then is if the baby is greater mass than 12 kilograms, it could cause the spring to break, and then the baby would fall on the floor. That would probably be a logical reason as to why this mass cannot be surpassed. Now, think about our knowledge from this question then. It's probably got to do with the spring. Now, why could the spring break? Well, the spring could break because it will keep on being extended, and then it will get to a point which is called the limit of proportionality, where it would just remain extended even though there's no force attached. So then the spring would become useless, and then the baby bouncer would become useless. Seven point two. In positions A and B, the baby is stationary. Describe the energy transfers as the baby moves from position A to position B. So the baby is not moving, that's what stationary means, at position A and position B. So we're thinking about energy transfers now. Now remember, we've identified the spring that's involved in this situation. So whenever we think about springs now, the energy that we should be thinking about is elastic potential energy. Now remember that the elastic potential energy is only going to increase when a spring begins to extend. Now, if we look at position B, the baby appears to be touching the floor. So that would probably mean then, if the baby is not moving and the spring is extended, that means that elastic potential energy is at its greatest value. But we need to describe from A to B. So if A, the baby is above ground, and B, the baby is touching the ground, that means that the baby has moved downwards. So if the baby has moved downwards, the energy that we should be thinking about to do with movement is kinetic. So that must mean then that from A to B, there's been a transfer of kinetic energy to elastic potential energy. But position A, one more time, the baby is above ground. If the baby is above ground, the energy that we should be thinking of there is gravitational potential energy. So what has appeared to happen then is, at the beginning, position A, the baby has gravitational potential energy, but then as the baby moves downwards, that gravitational potential energy is converted to both kinetic and elastic potential energy. But when we get to position B, because at position B the baby is not moving and is touching the ground, there shouldn't be any kinetic energy, it should just be elastic potential energy. So let's formulate our answer with that. Position A is gravitational potential energy. As baby moves downwards, this is transferred to kinetic and elastic potential energy. At position B, it's only elastic potential energy. Seven point three. In one position, the extension of the spring is 8 centimeters. The elastic potential energy stored by the spring is 4 joules. Calculate the spring constant of the spring. Use the physics equation sheet. 4 marks. So looking at our physics equation sheet, which equation includes elastic potential energy, extension, and spring constant? Our equation will be, to calculate elastic potential energy, that would be half, 0.5, multiplied by our spring constant, multiplied by our extension squared. So we just need to find those values from what we've underlined now. Our elastic potential energy is 4 joules. It's going to be equal to 0.5 multiplied by the spring constant, which is K, which we do not know, which we need to calculate. And we need to multiply that by the extension squared. The extension here is 8 centimeters. But the problem is our unit we're not happy with. It needs to be converted to meters. So to convert centimeters to meters, we need to divide by 100. So 8 divided by 100 would be 0.08. So we need to square that. We must not forget to square the extension. So if we rearrange all of this now, to find the spring constant, it would be 4 divided by 0.5 multiplied by 0.08 squared. Plugging that into our calculator, we will come out with a value of 1,250 newtons per meter. Question 8. Scientists developed new models of the atom as new particles were discovered. 8.1. Draw one line from each particle to the year it was discovered. So, we need to think about the development of the atom and which of these structures was identified first, and then going in chronological order. So, thinking about first, our main model that was devised first was our plum pudding model, which highlighted the fact that there were negative particles that were embedded in a ball of positive charge. And these negative particles were the electrons. So that was our earliest time, which is going to be 1897. Following on from that, we then had our alpha scattering experiment, and then from there we realized that there's going to be a positively charged nucleus which is in the center of the atom. So that would be 1911. Following on from that, we came to the conclusion that there's going to be a positively charged particle, which is the proton, and that would be in 1920. And then we have the understanding from Chadwick that there is a neutron, and that is 1932. The nucleus was discovered using an alpha particle scattering experiment. Alpha particles were directed at a sheet of gold foil. Figure 8 shows the paths taken by 7 alpha particles, A, B, C, D, E, F, G. (8.2) Explain why alpha particle A takes the path shown in figure 8. While looking at alpha particle A, we can see that it is fired at the gold nucleus, but when it approaches it, it then moves away. Why is that the case? Well, thinking about our structure now, it's a gold nucleus which is used. Now, what's our nucleus made from? Protons and neutrons. Remember that the neutron doesn't have a charge. The protons do. So that means overall, this gold nucleus has a positive charge. The alpha particles. Now remember that an alpha particle is the same as a helium nucleus. So that also means that it has protons and neutrons, neutrons with no charge, protons with positive charge, so also overall is positive. So that means then that they have the same charge. And we can say that for our first mark now. Both alpha particles and gold nucleus has a positive charge. So what does this mean now if they have the same charge and they go near each other? There's going to be repulsion, like charges repel. (8.3) Explain why the path of alpha particle B is more tightly curved than the path of alpha particle C. So let's go and compare both of them. We can see it's more tightly curved, definitely. But why might that be the case? Well, let's focus on the position. Looking at B, it is closer in its path to the nucleus than alpha particle C. Now, why is that going to be important? Well, remember that this gold nucleus has a positive charge. Now, if it has a positive charge, that means that it's going to generate an electric field. And anything that also has a charge that enters that field is either going to be attracted or repelled by it. Now, looking at B, as we said, the path of B is causing it to be closer to the nucleus than C. So that means that it's going to be closer to the electric field than C. And B is an alpha particle, so that means that it will still be repelled, causing it to move away. But because C is also moving away, we can say then, to compare them, that B is going to experience a stronger field or stronger force of this electric field than C. So formulating our answer now, the first thing that we want to say is that B is closer to the nucleus than C. Now, because it's closer to the nucleus, it will experience a stronger force from the electric field. (8.4) What can be deduced about the atom from the paths taken by alpha particles D, E, F, and G in figure 8? Tick one box. So let's look at the paths of D, E, F, and G. They're just straight. So there's no repulsion that's occurred. Well, what does that tell us then? The atom contains a nucleus. No, that doesn't give us any information about that. Remember that we just analyzed A, B, and C, and we know that there's repulsion that's occurred due to the proximity of those particles to the nucleus. The atom contains protons, neutrons, and electrons. Well, it doesn't tell us any information about the neutrons and electrons. We have some idea about the protons due to its positive charge, so it's not going to be that. The atom is mostly empty space. Well, let's look at the nucleus. Remember that it's directed at a sheet of gold foil, so it means it's got to be made up of gold atoms. So if the nucleus is at this position here, then everything else is part of the atom. So if it's going straight through and there's no repulsion, that must mean that most of the atom is empty space. (8.5) How is the Bohr model of the atom different from the nuclear model of the atom? Well, that means that we have to compare these two models. They both at this point have an understanding of a nucleus. They both at this point have understanding of electrons, protons, and neutrons. However, Bohr's understanding from his work was to give us a concept of shells and energy level or energy levels. But what the idea from Bohr's experiments was that these shells and the electrons within them are at certain distances from the nucleus. What we understand now is that the electrons, they can orbit the nucleus by a range of different distances. So we just need to state that. 8.6. Explain how an electron can move up and down between energy levels in an atom. So, this is our nucleus, and here is one shell, and here is another shell. The question is asking us, how then can we have an electron to move down or up an energy level? Now, the reason why is to do with electromagnetic radiation. Remember, the electromagnetic radiation is part of the electromagnetic spectrum. And what atoms are able to do is atoms are able to absorb this electromagnetic radiation, but they're also able to emit the electromagnetic radiation. Think about gamma radiation, part of radioactive decay. That means that an atom or nucleus is emitting gamma radiation, and that is our type of electromagnetic radiation. Highest energy, highest frequency. So what will happen if an atom emits electromagnetic radiation? Well, it means it's emitting energy. So essentially the atom is losing energy. So if it's losing this energy, that means it's going to cause the electrons to move down an energy level. So what we can say is moving down energy levels is the result of the atom emitting electromagnetic radiation. And we can just say the opposite. So moving up energy levels is the result of the atom absorbing electromagnetic radiation. Question 9. Figure 9 shows air being pumped into a car tire. 9.1. Complete the sentence. Air particles in the tire move quickly in blank directions. So if we were to pump air into a tire, remember that air is a gas, so that means the particles are able to move freely. You cannot predict the direction at which these air particles will be able to move because they're able to move freely. So if we can't predict their directions, that means that it's random. 9.2. When the tire is at the correct pressure, pumping more air into the tire causes the pressure to increase further. The volume and temperature of the air in the tire do not change. Explain why pressure increases as more air is pumped into the tire. So imagine that this box here is our tire. We have some air particles that are in there. As we said from the previous question, the air particles are going to move freely in random directions. Now every time that they do that, they're going to collide with the walls of the tire, and they can collide with each other also. But what's going to happen when you pump more air into the tire? If you pump more air into the tire, that means that you're going to have a greater number of air particles. And if you've got a greater number of air particles, you should then expect the number of collisions to increase. So the collisions between the particles themselves will be more frequent, and the collisions between the particles and the walls of the container, the walls of the tire in this case, would be more frequent also. So we just have to state first that if there's more air in the tire, there'll be a greater number of air particles in the tire. And what that then means is that there'll be more frequent collisions between particles and walls of the tire. Remember, the temperature and the volume are not changing, so the only thing that is going to change is the number of air particles. 9.3. The air pressure in a car tire changes if the temperature of the air in the tire increases. Explain why. 4 marks. So this time we are talking about the temperature. So we're keeping the number of air particles the same in the tire. So there's going to be an increase in the temperature. So that means thermal energy is going to increase on this tire now. So what does that mean is going to happen? Well, if we start at the beginning, if the temperature of the air is increasing, then what that could cause then is the thermal energy to be absorbed by the walls of the tire, and then that could be transferred inside of the tire itself, and then that could then be transferred to the air particles themselves. So that means all of these air particles that are inside the tire already, they're going to be absorbing the thermal energy, and then they're going to move faster. Now remember, if particles are moving faster, the type of energy that they're actually gaining will be kinetic energy. So let's start there. The air particles gain kinetic energy. Okay, that means that they will move faster. Now again, just like our previous question, if these air particles are going to gain kinetic energy and move faster, what will then increase as a result? It will be the number of collisions. So there will be more frequent collisions once again. What is it going to be? Collisions between the particles and the walls of the tire. Now we've only got 2 points now. We need to gain another 2 points. We have to explain what's going on now. Well, why is there going to be a change in the pressure? Well, what is this change in the pressure actually going to be? They've said the word change, but change could mean there's an increase or a decrease. Well, if there's more frequent collisions between the particles and the walls of the tire, this means that every time a particle collides with the walls of the tire, a force will be experienced. The particles will exert a force on the wall of the tire, and the walls of the tire will exert a force on the particle itself. And that, as a result, is pressure, because pressure can be calculated, and this is really paper 2, force divided by area, that equals the pressure. So remember that we're talking about the temperature, so the volume of the tire is not increasing. So this area actually remains the same. What is actually increasing is the force in that certain area. So let's explain that to gain our 4 marks now. So the first thing that's going to be then is there'll be a greater force remember, our pressure is calculated in force divided by area. So a greater force in a certain area leads to a increase in the pressure.